This is joint work with David Shannon, who chaired the last session. And I want to apologize in advance that I'm actually not going to play any music or sound or whatever. I've given a lot of computer music talk over the last few years. And I've always played something, but not this one, so sorry.
Boo.
Warning you ahead of time. So, what are we trying to do here? I guess a goal of mine for many years has been to try to figure out a really elegant way and elegant in many dimensions of composing various media types. It could be sound, video, animation. It could even be robot motion. So the idea is we want something that's simple. We want a beginner to be able to use such a system. Efficient means that it runs fast, that we can do efficient transformations on whatever the representation is. Elegant in the sense of concision and inconspicuous. And sound, not in the sense of musical sound, but in the sense of having strong mathematical properties. So one approach is something that I started, I guess, 10 years ago now, something that I called polymorphic temporal media. And this is just a brief overview of that particular approach, and the purpose of this paper is to show an alternative approach. So what is polymorphic temporal media, or PTM? The idea is that there's a notion of a neutral value, which means, say in the case of music, silence, or in the case of animation, it would mean a blank frame, an empty frame, transparent frame. And a set of primitive values, for example, notes in music or video clips in the case of video. And then two ways of combining these things. So it's really a very simple system. And one way to combine them is sequentially in time, and the other is in parallel. So this is really the essence of PTM, but it's also the essence of both Haskell and interpreting. All the code and all of the examples and everything really ultimately boils down to doing this sort of thing at the lowest level. So in terms of having nice properties, PTM actually, I think, does pretty well. There's a set of various algebraic properties like the associativity of both sequential and parallel composition, and the commutativity of parallel composition, and so forth. There's a nice duality law here, which I won't get into, but the bottom line, there is a set of axioms that can be shown to be not only sound, but complete, which relies on the notion of normal forms and things which we won't get into, but I was pretty satisfied with this work, and not only having these strong algebraic properties, but PTM is polymorphic, as I mentioned earlier. It can be used as a thing that you could argue that it's simple and elegant, and it's also efficient. So, however, PTM has its shortcomings. A couple of these things have bothered me over the years, but I was pretty satisfied with the design in any case until I met David. And then things changed a little bit. But what are the shortcomings? Well, first of all, semantically, the parallel composition operator is a little bit problematical in that it requires some kind of interpretation. You have to decide if you're playing two things in parallel, if you're starting both of them at the same time, which is what most of us would think about doing. But if you think mathematically or algebraically, that's not the only way to do things. Maybe they should end at the same time, or maybe they should be centered, or maybe you should require that they both have the same duration so it doesn't matter. Whatever. So that always bothered me a little bit, that we had this choice, if you will. It's better to have something that's doesn't allow that flexibility. If you want to, well, I don't call it flexibility, I call it looseness, if you will, in the semantics. And in terms of expressiveness, another shortcoming is that in the case of practical applications of PTM, say concretely music or animation, there's this problem that you kind of miss the logical nature of a composition compared to just a brute force actual implementation. So this will become clearer in a minute, but let me give you one example, since music has been a big theme here, is that if you have a pickup into a measure, and you're thinking in terms of measures, then the logical structure of what you have is something that is the measure, and the pickup is this sort of little thing on the front. Similarly, you might have something on the end. So that notion of logical structure is missing in PTM because you have to include that beginning pickup or anacrusis with the measure, and then you have to figure out how to align things with the thing you're proposing with in parallel. So a solution is what we call tiled PTM, and this was motivated last year. The first part, David gave a very nice talk on something called the T-calculus, which at least conceptually eliminates these shortcomings. But the T-calculus also has some shortcomings. You can view the T-calculus as a tiling of values in the one dimension of time. Okay, so here's that time theme again. But it does not have, or did not have an implementation, or does not have an implementation. It is a bit constrained in power in terms of how it's set up to be specifically representing finite state transducers. And David made a nice connection to inverse semigroups, which wasn't quite as strong as it could be. And what we've developed strengthens that connection. And its recursion scheme that would allow creating infinite tilings, if you will, is a bit weak. So what we've done is taken the T-calculus and combined it with polymorphic temporal media to create what we call tiled PTM. Let me describe that in more detail. In summary, though, our contributions are the design of this new framework that combines the two ideas, tiled PTM, the discovery of new algebraic properties, in particular stronger connection to inverse semigroup theory, and the exploration of effective recursion schemes, which I won't say too much about in this talk, but is in the paper, and we've implemented this in Haskell and in particular in Turkey. So what's the idea here? The basic idea is that a tiled PTM has two synchronization marks. One that we call pre, and the other one that we call post. So if you think of this M as being the underlying media value, okay, then there is a notion of the actual start of that thing, but there's also the notion of a logical start and a logical end, and then you have the actual end. And the whole idea is that with these pre and post markers, if you will, then you can align things in time based on the logical structure rather than the actual structure. So it's a pretty simple idea. The key, aside from that definition of what tiled PTM is the notion of taking the product or the composition of two of these. Now in PTM there were two. One was sequential, the other was parallel. In tiled PTM there's just one, and we've represented here with the percent sign. So M1 composed with M2 is a tiled PTM that is the product of the two underlying tiled PTMs, M1 and M2. And doing so involves two steps. One is synchronizing the logical marks, timing of the two underlying values, and the other is the fusion of the overlapping content of M1 and M2. And that fusion is domain specific. So in the case of music, it might just be you hear both things happening at the same time. In the case of animation, that there needs to be some notion of how images are blended together and so forth. Okay, so a lot of words that are best really explained by a diagram. So here we have M1 and M2. Each of them has a different pre and post mark. And then that blue line says this is how we do the product. We basically align the logical start time of M2, which is this pre-2 thing, with the logical end time of M1, which is the post-1 time. Yeah?
Does the logical time have to be properly nested within the actual
No.
time?
These can be in any order, and in fact, they pre and post can be reversed, and I'll show you that shortly. So if you imagine doing that, what we're doing is taking M2 and shifting it so those things line up. And if we do line them up, I represent that here with this blue guy here, then the pre-mark for the result is the same as the pre for M1, and the post-mark is from the actual time of M1 all the way to the post time of M2. Okay? So that's what the logical product is.
Can you explain a bit more about that? I understood all of the pre and post bit.
I'm sorry, say it again?
I understood everything into the pre and post bit, the combination. Why is the post line that way?
What's the idea? So the idea is to think of having M1 happen first, and then M2 happen second. So the when you do this composition, remember that this could be way back here. This anacrusis of M1 could be way back here, but pre still is this beginning of M1. That helps. So a key point, which I've already said, is that the underlying values could overlap. And in that sense, it's neither a sequential nor a parallel composition. It's actually both because of this overlap. And indeed, one could define PTM's sequential and parallel compositions in terms of percent. Okay, and so just to again highlight the generalization which relates to some of the questions being asked. In a given tile, pre in fact may be greater than post, in which case one simply follows the same rules blindly, if you will. And now though, in this case, we have pre, but we still align it with post. Pre2 aligns with post1, but now it amounts to shifting M2 this way. So this is where the synchronization happens, and you get this result here. Okay, so the music, in the case of music, begins here and ends here, and the result that you hear is the fusion of these two guys here. Okay, so this is, you got to understand this. If you understand this, you understand, in a sense, everything about how PTM. If you don't understand this, then you're missing.
So that means it's not the case that the logical content of M1 and M2 is all within the logical content of their composition. The
That's
logical
right.
content might exceed that here.
Yes. Right. Okay. So, with a suitable notion of observational equivalence, which is described in the paper, then one can show that this tile product is, in fact, associative, which is, you would hope for that to be the case, and it is the case. And it turns out that a neutral value of duration 0, which we represent as R0, is a 0 in the algebra, so that R0% T is the same as T, but the same as T% R0. So tau PTM is the monolith. But we're going to do more than that. First, let me introduce a couple other operators. There's the notion of primitive monomorphic values, which say in music you want to have notes. So this is a simple way to do that in a concrete sense. But more importantly, there are some other operators. One's called reset, one's called co-reset, and the other's called inverse. And again, diagrams are best way to convey the semantics of those. At the top we have a tiled PTM. That's a pre and a post. So what reset does is it takes the post and aligns it with pre. It literally changes post to be the same as pre. Co-reset does the dual of that, if you will. It makes pre the same as post. Okay? So logically, both the reset and the co-reset don't really, in the case of music, say, play anything, because it's instantaneously, well, I guess it's playing, it's infinitesimally small, something or other, but it's zero, or the duration is zero. And what in does, the inverse, is flop the pre and the post. So now that pre becomes post, and that post becomes pre. Yeah?
Are any of these or all of these equivalent in your observational equivalence?
No, not in general. Okay? Yep. So, with that stuff, so this is the so I suppose I could have played this, although it wouldn't have really taught us that much. But it's an example of what I call modularity, what computer scientists call modularity. The whole idea of modularity, or one characteristic of modularity, is that when you compose some things together, if you make a change to one of the components, it doesn't force you to make changes to other components, right? That's kind of what we think intuitively about modularity. And this is demonstrating that PTM, in fact, is not modular. Okay, and it relates to the very first couple of slides where I said that I didn't capture the logical structure of things. So, for example, suppose we have two measures, I'm calling them M1 and M2. M1, again, to repeat the example earlier, is there's some notes, say, and then there's nothing, and then there's a pickup. So we have PM is, think of that as partial measure. We have some rest, or notion of silence, and then a pickup. And we're combining that, so combine those things together and call it measure one, and what we want is measure one followed by measure two. That's sort of fine. It doesn't really capture the logical structure in the sense that that pickup really belongs with M2, not with M1. So let's go with it anyway. If we were to lengthen the pickup, then we'd have to change that rest, maybe from D0 to D1, if we change the length of it. So that's not modular in the sense that we've made a change to one thing that causes a change somewhere else. In fact, if the pickup becomes sufficiently large, it will actually overlap the notes in the partial measure, right? How do you do that? Well, then we have to really change our structure a lot and create the partial measure by itself, the pickup by itself, combine them together in parallel before combining them with the second measure. Well, that's not good at all. It's more modular, but it still lacks logical structure. And the point is, with tiled PTM, we can write this. We have M1 followed by, if you will, and then what we do is a co-reset of the pickup. And that means the post and the pre get aligned, right? And then it gets aligned with the beginning of M2. So the logical structure here, or right here, is the logical start of M2, but now it has this anacrusis stuck on the front of it, and then we combine that with M1, and we're done. And the point is, I can change this any way I want, and this code is going to remain the same. So that's what I mean by modularity. Okay, so why this inverse operator? Well, first of all, using inverse, we can define reset and co-reset. And that's nice because we always want to sort of have the minimal number of operators, say. So in a sense, with inverse, we don't need reset and co-reset because we can define them in terms of inverse. But the other point is, this is where we make a nice connection to inverse semigroup theory. And remember, the inverse requires having what we call negative tiles in the sense that post happens before pre. So in inverse semigroup theory, the whole point is to have this binary operator such that these two properties hold. So for every x, there is a y such that x composed with y composed with x is x, y composed with x composed with y is y. Well, if you work out the algebra, that's exactly what in T does. So in fact, tau PTM is an inverse semigroup. Why is that important? Well, it's always nice to make a connection to some algebraic structure or whatever for mathematics. But it also allows us then to use inverse semigroup theory to, to have immediately various properties of whatever it is that is an inverse semigroup. And there are a couple of examples of that in the paper. I won't get into it, but that's the other advantage. So I'm going to talk about one other thing in my last couple of minutes, and that is recursive and infinite values, either in PTM or tau PTM. If we look at PTM for a second, so what does it mean to actually play something that has this temporal quality, right? So again, it relates to time. We need to be able to enumerate in time events that correspond to what it is that we're doing, whether it's an animation, or playing music, or controlling a robot. We need to be able to start at the beginning and say, okay, this is what's going on. So let's call that rendering. So we render a temporal value. We need to figure out what these things are. With polymorphic temporal media, it's actually very straightforward. So here's an example of a music value. So this is C4EN is the note C in the fourth octave as an eighth note. And it's followed by N. But N is this thing here. So we have this recursively defined infinite thing. And we do this sort of thing all the time in Utopia. And it's not a problem to implement that because you play C4, you see M, lazy valuation, if you will. It's like having an infinite list and everything works out fine. Even parallel composition is okay. As long as I can render M1 and M2 independently, right? I can do so, and then just do a time merge of those two enumerations, and I get what I want. So infinite, even if these guys are infinite, this algorithm, this strategy, if you will, works just fine. But with tidal PTM, we've got a problem, Houston. So here we have x equals, now that little t in the front just means it's a tile version of middle C, if you will. And if we're trying to emulate what I just showed you on the previous slide, we have a recursive definition of x. But the problem is that the percent is creating a single tiled object, and its post value is infinite, right? And this creates problems in actually enumerating the events that happen. And even a version where we reset x, which, if you think about it, is in the right direction of trying to solve this problem, because by resetting X, we're at least making a distinction between the notes. The reset value means that it's pre and post are the same, and we don't have this problem with post being infinite. But even enumerating that is a problem. And you can actually, if you think about it, forget infinite values for a second and just look at T1%, T2. The anacrusis here, if you will, could start before T1, right? So in order to enumerate this thing, or render it, we need to know everything about T2. And that's where the problem arises with the infinite values, because if this is infinite, we can't compute everything about T2. So what we've done in the paper, you'll see, I'm not going to get into details, there's a new operator called %/. I don't know how you pronounce it, but that's what it is. Which ignores the anacrusis in the second argument. And then we can make some progress in that this example, in fact, can be rendered properly. But now, this guy's not even associative. Okay, and we lose these nice algebraic properties. So it's perhaps a nice solution in practice, but not quite sufficient. In the paper, we explore this whole issue of finding the fixed point of a recursive equation in a more general setting and designing a fixed point operator that can do that. It's not completely satisfying, but it's a step in the right direction. So this is my last slide, in fact. The paper also talks about the implementation of PTM in Recursive, which we have used as a specification, which is a pretty common thing in the Haskell community. And we define a notion of observation equivalence using that notion, or that specification. We make formal this connection here that I mentioned earlier. And then there are various other operators that we also introduce that are handy in practice, but don't necessarily extend the fundamental power of things, but have interesting properties. And then there are some examples. So there you go. No music. Sorry.
What's the questions here?
So in your untiled PTM, you showed us an example of an infinite to the right piece of music, a note followed by itself. This N is a C followed by another copy of the same piece of music.
Right.
That one works fine, you say. You can render that. But there are still recursive ones you can write in PTM.
Of course.
Where the left recursion happens to the left.
Yes. Yeah, if you do left recursion, you're screwed.
Yeah. So we've got deeper problems with that, I think. There.
Oh yeah, yeah. No, I didn't mean to say that this solves everything. It still amounts to, can you enumerate in time? I mean, I think we need to more formally define what we mean by that.
Yes. So I mean, you can define infinite trees.
Yeah.
And with the associativity properties, you can reassociate them.
Right.
So that you don't have the leftmost leaves infinitely deep. That's a problem. That would be a problem if you did. But
yes.
You can reassociate with the apps so that all the leftmost leaves are finitely reachable.
Right.
But then, and presumably it's important that you kind of make progress in time.
That's right.
Through the tree.
And that's the key thing, is making the progress. And I should mention that that's not the only problem. If you just look at the duration component, you can write programs that, like Zeno's paradox, right? So there's an enumeration problem there as well. So it's a hard problem. Bill?
And I actually have two questions. I hope we could.
Go ahead.
The first one was, have you investigated the relationship to Brent-Jovi's diagrams? Because he uses a very similar definition to for composing diagrams. So each diagram basically has a local origin, and composition operator will compose the diagrams.
What's the reference there again?
It's really called Brent-Jovi. The library is called diagrams. It's a graphics.
Oh, but Brent, you already.
Yeah.
Oh,
Because basically, I use a similar definition in music, and I basically took it from Brent.
okay. I'll take a look.
I think Brent's copied it from Haskell.
Yeah, they're very nice. He's converting Haskell too.
We have a circular loop here.
And the second one was, what would you say would be the interpretation of these inverse values, whether the post is less than the tree? So for example, in a musical setting, will that amount to play the back chords or the sound back chords?
Yeah, so when pre and post are reverse, we don't really interpret that as things going backwards. It really has everything to do with the synchronization, not going backwards. But in the paper, I do talk about reversing the underlying media value.
Yeah.
And that amounts to lifting a reverse from the, let's say, the music domain into the tile PTM.
That would have to be a separate operation from
Yeah.
Yeah.
Yeah,
The code starts before the input finishes.
right.
I have one more question.
So that was very pretty. It's really nice to see that even something as pretty as PTM can be improved upon. The way in which you defined co and reset in terms of inverse requires a sort of idempotence.
Yeah. Good point. That's right.
And I was wondering what would happen if instead of using idempotence, you use negation. You think of the two amplitudes and you add them together. And now what you would need to do is t percent inverse, minus inverse of t, or inverse of minus t. And then they would cancel out and you'd still get these pseudo inverses.
Yeah. I'll think about that.
And I wondered if that could help with the slash operator that you described at the end, because now by using minus you can zero things out, right? There's something with zero amplitude instead of zero duration. And I wondered if that might be a better approach to the slash.
Maybe. I guess it's kind of a jump for me to think about changing amplitudes from dealing with just time.
It seems like
So we're trying to make this completely polymorphic. I'll have to think about it.
It's
Postulate to negation.
Polymorphic because all you need is a group, right?
Yeah.
Any group would do.
it seems to just make the parallel part carry an inverse as well, right? So if you have something that actually
Yes,
inverts,
right. So abstractly, you just assume that exists and you
Yeah.
lift it. Yeah. Thank you.
Entirely, I've done time actually, yeah. So, thank you very much.
Okay.